one of the main reasons that we use GPSR are that the models used by so they're interpretable or white box in the sense that we can understand how they're making predictions. So for fields like medical applications or mechanical engineering or theory, this can be important to get a sense of trust into what the model is doing. Furthermore, GPSR produces a population of equations rather than a singular model. So for example, the output of a GPSR run, for example, could be something like the figure shown on the right, where we have multiple equations in what's called a Pareto front. So each of these blue dots would be an equation, where the x-axis represents the complexity or expressiveness of the equation, and the y-axis would be the error. So you can choose among these equations rather than having to retrain a model each time you get multiple. Furthermore, since equations are generally simpler than other ML methods, they generally have smaller inference costs than them. And then this comes at the downsides that GPSR is computationally expensive, and that GPSR can take in the range of tens of hours and sometimes even days to train. So that's significantly longer than most machine learning methods. Furthermore, since GPSR is performing a random yet conducted search over the space of equations, since the space is so large, we usually constrain it in some way. And because of that, the models produced by GPSR are usually less expressive than other techniques.
They just comment if you can stand closer to the laptop, they can hear you better. And then also your slides are updating on Zoom, which I think means I don't want you to do things rather than use them.
Sorry about that. Okay. Yeah, I'll try to stand closer to the mic. Can you guys hear me okay and see the slides?
Yes, now I can see the slides is going.
Awesome, thank you. Sorry about that. Sure. This one. Very sweet. Thank you. Cool. Awesome. Yeah, if you can't hear me, just let me know and I'll try to stand closer. Thank you. Cool. So we use a open source framework for GPSR developed by NASA called Bingo. And the reason we use Bingo is that it's both performant, but also extensible for users so that they can customize the GPSR workflow to their needs without having to rewrite it. Furthermore, it also gives easy or turnkey access to state-of-the-art techniques so that users get powerful techniques without having to make them themselves. And the couple things we need to understand about Bingo are that it represents equations as directed acyclic graphs. So for example, the equation shown here is C0 times X0 plus X0 plus X1. And another thing we need to understand is that these equations can have tunable parameters. In this case, this equation has C0, which can be any numeric constant, depending on the data. And the way that these are determined are that before equations are evaluated, an optimizer will set the parameters to whatever best fits the data. Another thing we need to understand about Bingo is that it uses fitness functions. You can think of these as loss functions to be able to determine how well equations perform at a given task. The two that we'll be looking at are explicit and implicit regression, which are for finding explicit and implicit equations respectively. The former is a typical way of measuring the loss is simply to evaluate the equation and then just measure the difference with an expected value. However, if we can't use this approach for implicit equations since they're of the form f of x is equal to some constant. For example, think of the equation of a circle that's x squared plus y squared is equal to r squared. So if we let r equal 3, then we get an equation that always evaluates to 9. And if we were to use explicit regression in this case, we would find equations like 9 is equal to 9, which isn't what we want. We want the equation x squared plus y squared is equal to 9 instead. So there are multiple ways of dealing with implicit equations, one of which is using the derivatives of the equations to define loss. another of which is to measure the distance between the point and the orthogonal to the equation. And I'll be talking about the former approach later. So that covers the basic concepts that we need to be able to understand the modifications we make. So we modify GPSR to be able to evolve strongly typed equations. And this just means that the equations follow a particular typing system. In this case, I'll be talking about what I'll term as the linear algebra typing system, which just means that the equations produced by strongly typed GPSR are a system of equations, or can be thought of as tensor expressions. So this is possible within normal GPSR, but a user would have to run a GPSR run per equation and then do the constraints between the equations themselves, which is both tedious and error prone. So the motivation behind strongly typed GPSR is to have a system that can do this in one go. So the way we modify GPSR to be able to have strongly typed capabilities is that we modify the equation generation and modification systems. And the backbone of this is a system that I'll call the type verification system, which I'll go over now. So consider we had the equation C0 times X0 plus X1, where this multiplication is a matrix multiplication. And we wanted to ensure that this equation fulfills our linear algebra typing system, or in other words, that the dimensions of the operators are compatible. So in this case, if we were given the shape C0 is 4 by 3, X0 is 3 by 5, and X1 is 4 by 5, we can walk up the graph and ensure that the dimensions of each operation are compatible. So for example, for the matrix multiplication, we need to ensure that the inner dimensions are the same. In this case, they are. The 3 is the same in both operands. And then for the addition, since both operands have the same shape, then this overall equation fits within our given typing system. However, if instead we were to have this equation here where we've changed the shape of C0 to be 4 by 3, then we can see in the matrix multiplication that the inner dimensions don't match. Therefore, this particular equation does not fit within the linear algebra typing system. So we use this type verification system to ensure that equations produced by GPSR always fit within the typing system that we specify. There are other approaches for doing this, such as dynamic programming, which is presented in Montana's strongly typed genetic programming. For simplicity, we use what I'll call a smarter brute force approach, which I'll explain in depth in the next slides. But the basic concept of it is that we generate a candidate equation. If it fits within the typing system, you keep it. Otherwise, you try to fix the portions that don't fit within the typing system, or throw it out and regenerate a new equation. Similarly, for the equation modification, if we try to change an equation and it violates the typing system, we try to fix that. Otherwise, we throw out the modification and regenerate a new one. So this approach works for our cases since the linear algebra typing system is simple enough. However, for more complex typing systems, this is untenable, and we'd recommend using something like the approach presented by Montana. So to describe what I mean by smarter brute force, instead of just randomly generating operators and hoping that they fill the typing system, we can take into account the context of the currently generated graph. So for example, here, consider that the top of the graph has been generated. We don't know what it is, but we have this defined portion of the graph below it where we have the middle matrix multiplication, and we have one of the operands is X0 with the shape of 3 by 5. And then we want to generate a node with this question mark here. So instead of just randomly generating something, if we choose to use a constant or some other operator, we can enforce that the inner dimension matches the other operand instead of just randomly trying things. That way, we ensure that this equation is valid. Furthermore, if we have more context about the whole equation, we can determine what this outer dimension of the C0 will be. And so that's what I mean by smarter brute force. We're not just randomly generating things, we're also taking into account the context of the already generated components. So that brings us to our applications for strongly typed GPSR, which are elasticity tensor modeling and yield surface mapping. I'll cover the first of which now. So Elasticity tensor modeling is modeling the C tensor shown in the relation here, which describes the stiffness of a material, and it relates how much a material, when a material is stretched, to how much stress it undergoes. And the reason that we're interested in modeling this elasticity tensor is that it's useful for optimization routines such as topology optimization or designing metamaterials. And so we want to be able to develop a model for the C tensor in terms of the design parameters of some material. So we'll show that strongly typed GPSR is effective at this in two different cases. However, before that, in order to ensure that the models produced by strongly typed GPSR are physically admissible, we know from continuum mechanics that C must be symmetric about the main diagonal. Furthermore, depending on material symmetries, C could also have different symmetries. For example, in this work, we'll be considering materials that have what's called a cubic symmetry, in which case the C tensor has this form. And so in order to enforce that strongly typed GPSR produces equations that abide by these symmetries, we enforce that parameters within all the equations also do so. The way we do this is that we only give optimizers access to the parameter values that it needs. For example, if we wanted to ensure that a parameter was symmetric about its main diagonal, we would only give access to the upper triangular portion of the parameter, and then before that equation was evaluated, we would convert that upper triangular matrix into a full symmetric matrix. We can do a similar thing with the cubic symmetry case here, where we only give an optimizer access to C11, C12, and C22. This works in the cases presented since we only have scalar and vector inputs. However, if we were to allow tensor inputs or matrix multiplication, that could break the symmetry, in which case we recommend that a user would use a symmetric typing system or a custom fitness function. A symmetric typing system would mean that only operators that continue symmetry would be allowed, and then a custom fitness function would punish models that aren't symmetric accordingly. So also to get an understanding of how well our models relate to material parameters, we can break C down into three fundamental parameters: Young's modulus, Poisson's ratio, and shear modulus. And this is just to give a more intuitive understanding of how well our model is modeling the material, since it's hard to interpret the C matrix altogether. So Young's modulus is a measure of the stiffness of a material if you were to pull on it. Poisson's ratio is how much the material thins out if you stretch it. If you think of like a rubber band, if you were to stretch a rubber band, it thins out. And then shear modulus is if you were to take a cube of material, how hard it is to slant that material. So these are just parameters that we'll use to compare our models with the actual material behavior, such that we get an understanding of how well our models perform. So the first test case we'll be looking at is modeling the elasticity tensor of the octet truss microstructure shown on the right here. And we're interested in measuring or modeling the elasticity tensor of this microstructure based on the density of these supports. So at the top, we have a truss microstructure with less support, and at the bottom, we have it with thicker supports. And that relates to the density of the bounding unit volume around the microstructure. And so we'll call that the density of the microstructure. Furthermore, we also want to be able to change the material that the microstructure is made up of. So in this case, we'll parameterize that material by its Poisson's ratio if it was a solid cube. So the Poisson's ratio of the solid cube will be some value, and when we change it to the truss microstructure, we'll have a different value. The reason we're interested in this is that having a model for the elasticity tensor in terms of the design parameters is useful for optimization routines and for making metamaterials. A metamaterial is a material that has properties that often aren't found in nature and is made by taking these microstructures and forming them in a periodic way. And so in order to aid with the design of metamaterials, we can provide an optimizer with a model of the elasticity tensor. That way it doesn't have to perform a simulation every time it makes a design change. So we generated data from 10 different relative density values using 3 different materials for these octet truss microstructures, and then ran strongly typed GPSR to model the elasticity tensors with respect to those. And we get the following model here, which is pretty gnarly, however, it is accurate. We note that it follows the cubic symmetry form that we described before. Furthermore, if we wanted a simpler equation that was less accurate, we could also choose that from the population like I showed in the beginning. Just to give an intuition of how well this model performs against the actual data, I have these results here. We're starting from the left, we have Young's modulus, in the middle we have Poisson's ratio, and then on the far right we have shear modulus, plotted with respect to the density of the truss microstructure. The different colors represent the different Poisson's ratios of the solid cube of material that the truss is made up of. And then the points are the actual data and the lines are the model data. So as we can see, and this as quantified by the average relative percent error, this model fits the data relatively well. So that brings us to our second test case, which is the complex, a more complex microstructure in 2 dimensions instead of 3 this time. And this is formed by 2 different design parameters, which I'll call alpha and beta. And these design parameters are used in the equation shown here to generate a void within the 2D element, which I'll show in a second. And we generated a 10 by 10 grid over the range -0.3 to 0.3 for these alpha and beta values, and then use strongly typed GPSR to model the elasticity tensor in those cases. So to give some intuition about what those alpha and beta parameters do, we have different alpha and beta parameters on the slide here, where as you vary those parameters, this void changes shape. And if any of you were at Hong Sup's thesis proposal, this is a simplified case of that same microstructure. So after running strongly typed GPSR for 500 generations using, we get the following model or one of similar accuracy. And to give an understanding of what that model looks like compared to the data, we have these plots, again, similar to the previous test case. One far left, we have Young's modulus. In the middle, we have Poisson's ratio. On the far right, we have shear modulus plotted against the design parameters. The points are the actual data, and then the surface in this case is the model. And you can see that the data fits relatively well, but it's hard to get a quantitative understanding of that. So this plot shows the relative percent difference between the predicted and actual values. And these are in the tens of percents, as you can see here. And the average errors are listed below each plot. So that brings us to our third application, our second application, which is yield surface mapping. And yield surface mapping is, or I should walk back. A yield surface is a surface, and in this work we'll consider it in 3D space, that defines the plasticity behavior of a material. And we propose a way that maps a yield surface onto another. So the motivation behind this is that some material simulation software can have a model of one material, and instead of having to change that model for every different material, we can provide it with a mapping that takes its existing model and maps it to another material rather than having to change that underlying model. So we propose an extension to a prior work called the tensor transform method, which I'll describe. The tensor transform method takes or finds a way to map a static yield surface onto another one. However, we're interested in extending this to the case where the yield surfaces can change or expand. The tensor transform method is based on the idea that we can represent a yield surface in the form shown here, where the sigma vector is the void principal stress, P represents the yield surface, and if we set P equal to the form shown on the bottom left, we recover the von Mises yield surface, which is a fundamental yield surface. We can think of it as a cylinder in principal stress space about the 1, 1, 1 vector, just for a mathematical view. And then the tensor transform method formulates two different mapping tensors, A and B, which go from a given yield surface to a real yield surface and backwards respectively. And the tensor transform method forms this objective function shown here, which basically states that when we take the prescribed or given yield surface and we map it to the real space, they should behave the same. So we're interested in extending this tensor transform method to a evolving yield surface. And to do so, we have to be able to find these A and B tensors with respect to some state parameters. And we propose doing this in two different methods. The first of which I'll call a direct method, in which we take the given yield surface and then we try to find this A tensor that goes to the real space and fits the data points. And the other method, which I'll call the two-step method, which goes from the real data points, fits a yield surface in the real space, and then tries to find the B tensor that goes back to the prescribed space. So at the heart of both of these methods is finding a yield surface that fits the data. So if we look in the two-step method, we fit data for these real points. And in the prescribed method, we want to quantify how well that mapped prescribed yield surface matches the points. And in order to do so, we need a way of measuring the accuracy of the implicit equation, which, as I mentioned before, we use Bingo's implicit equation, which will use the idea of derivatives, which I'll explain. So the Bingo's implicit regression uses the idea that points can be viewed as trajectories moving throughout time. So for example, in the case of an expanding circle, we could have points along the circle, and if that circle is expanding throughout time, then those points will have trajectories as shown on the right. And then the goal is to find an equation whose derivatives are orthogonal to those point trajectories. So that's what the numerator of this law shows. And then the denominator is a way to regulate against the trivial solutions I talked about earlier. So for example, again, that x squared plus y squared is equal to 9. We don't want to find 9 equals to 9. That's what that denominator does there. So this implicit regression metric was formulated for finding yield surfaces. However, for our cases, we had to modify it to work for our cases. And that's because we had this issue presented here, where if we generate proportional loading data from the von Mises yield surface, so shown in these blue points, and then we calculate the derivatives between them, and then we can recover this plane solution, which according to the previous metric fits the data. However, instead we want a cylinder about the data shown here. And so one of the ways that we regulate against this plane solution is to also include the derivatives within each contour rather than all between them. So if we include both, then we get rid of that plane solution and cover the cylinder shown on the right. Another way of regulating against that solution is to incentivize P to have varied entries. And we do this through some coefficient of variation term within our fitness or loss function. And the reason we do this is that if P has all of the same entries beta, then we get the equation of a pair of planes, which results in the plane issue. And so we want P to have different entries, essentially. So with that background information, we can move on to the three test cases that we look at. The first of which is taking a von Mises yield surface with hardening. So what that is that cylinder we saw before. If we were to look down onto the 1, 1, 1 vector, then we would see a circle, and a von Mises with hardening yield surface will basically have that circle and expand with respect to some state parameter. In this case, we'll call it epsilon Vm. So we prescribe a linear hardening or linear expansion rate with respect to epsilon Vm and get the data shown on the right, where we have these expanding circles. Again, this is a view of 3D space, and we're looking down onto the cylinder. So we generated 14 of these expansion values with 50 points per value, and then used strongly typed GPSR to try to map all of these von Mises values down to a singular cylinder. And so When doing this, strongly typed GPSR is able to recover a mapping that you can find algebraically. So this has no error because we don't have noise, and it maps to a static von Mises yield surface with a radius that I'll show here. But to give some intuition into what this model does is that the blue points are the real data that we saw earlier. And then if we use the mapping that strongly typed GPSR found, or that you can also derive algebraically, we can map all of those points into the singular von Mises shown in orange. And an alternate way of looking at this is we can also take that singular von Mises yield surface and use the mapping to go into the real space, which is shown on the right. And if we do that, then the yield surface fits the data perfectly according to our metric. As an extension to this test case, we looked at an anisotropic version where the Hill yield surface shown here is basically an anisotropic version of the von Mises yield surface. We have a very similar setup, the notable difference being that instead of mapping down to one cylinder, we map to just a cylinder and we don't care necessarily about its radius. So we generated data with these parameters, which define the anisotropy, which I'll show in a second, and then 10 different expansion values in this range with 50 points per expansion value. And then we try to use strongly typed GPSR to find a mapping from this data to, again, a von Mises cylinder of some radius. So we recover this mapping within tens of generations or one with similar accuracy. This particular model has a mean squared error of 0.0008, according to our previous definition. And the results of that are shown here. So we see that the data in the real space in blue is mapped to the von Mises cylinders in orange. And then if we go back from the von Mises up to the real space, that's shown on the right, then the mapped yield surface fits the data relatively well, as quantified by the error in the previous slide. So it brings us to our third test case, which is taking a simulation of stainless steel and doing a similar thing to the previous test case, except that we don't know the underlying yield surface. We have to find it. And so we generated data with 6 different epsilon VM values in the range of 0 to 0.125 with 37 points per each of those values, and then use strongly typed GPSR to find the mapping from this simulation data down to a von Mises cylinder of some radius. And using that, we recover the mapping shown here, which has a mean squared error of 0.0108, and other runs recover similar mappings with similar accuracy. So to show the results of this mapping, we have the real data shown in blue mapped to the von Mises data shown in orange. Then again, if we go backwards from the von Mises yield surface to the real space, that's shown on the right with those purple lines, and that fits the data relatively well, as again quantified by the error on the previous slide. So that brings me to my conclusion, which is that we were able to modify GPSR to be able to evolve strongly typed equations. In this case, we were interested in finding tensor equations or systems of equations. And we applied this to elasticity tensor modeling in 2 different microstructure cases, as well as yield surface mapping. And while the presented problems may seem simple, they can also be extended to other more complex, more interesting work, such as finding piezoelectric constitutive models is very similar to modeling elasticity tensors. So with that, I'd like to give thanks to my advisor, Professor Hochhalter, for his advice and guidance, as well as to Professor Zhe and Kirby for getting me interested in research in the first place. I'd also like to give thanks to Brian, Hongsup, and Carl for helping me understand mechanical engineering concepts, as well as for generating data. And finally, I'd like to give thanks to Jeffrey Bomarito for his insights and work into Bingo. So with that, I'd like to say thank you, and I'd be happy to take any questions.